Here we discuss the next topic on electrostatics, the electric field. So consider two charges, Q1 and Q2, separated by a distance R. So we know that there is an electric force of interaction between these charges Q1 and Q2. Even though they are separated by a distance R, there is no physical contact between those two charges. Even then, there is a force of interaction between them. So those charges interact through the electric field. So electric field is defined as the region or space around a charge where another charge experiences a force of attraction or repulsion. So even if there's no charge around this charge, there will be an electric field around this charge. So around any charge, there will be an electric field. So the strength of this electric field can be measured by placing another charge in the electric field. So the region or space around this charge where another charge experiences a force of attraction or repulsion is called the electric field. So in order to measure the strength of electric field, we place another charge. It is charge Q naught. Then there will be a force experienced by this charge Q naught. Then the intensity of electric field is defined as the force experienced by the charge Q naught divided by Q naught. So electric field intensity is the force experienced by a unit positive charge. So suppose we have to measure the electric field intensity at a point P, then it is the force experienced by a unit positive charge placed at that distance, and therefore we can write F is equal to Q0 times E. So the force of interaction at a particular point P is the charge at that point multiplied by the electric field intensity at that point. So from this equation we can see that the unit of electric field intensity or the unit of the strength of electric field is given as Newton per coulomb. So this electric field intensity is a vector that measure the strength of the electric field. So we know that around every charge there is an electric field. So the strength or the intensity of the electric field is measured by a vector called electric field intensity. So generally this vector is termed as electric field. ആ റീജിയനെയും നമ്മൾ ഇലക്ട്രിക് ഫീൽഡ് എന്നാണ് പറയുക. ഈ വെക്ടറിന് ഇലക്ട്രിക് ഫീൽഡ് ഇന്റൻസിറ്റി എന്നോ സ്ട്രെങ്ത് ഓഫ് ഇലക്ട്രിക് ഫീൽഡ് എന്ന് പറയും. പക്ഷെ നമ്മൾ അതിനെ ജനറലി അബ്രീവിയേറ്റ് ചെയ്തിട്ട് ഇലക്ട്രിക് ഫീൽഡ് എന്ന് പറയും. സോ ദി സ്പേസ് ഈസ് കോൾഡ് ഇലക്ട്രിക് ഫീൽഡ് ആൻഡ് ദി വെക്ടർ ഈസ് ഓൾസോ കോൾഡ് ദി ഇലക്ട്രിക് ഫീൽഡ്. സോ the strength of the electric field is the force experienced by the unit positive charge placed at that distance. Now we have to find out the electric field due to a point charge. So suppose we have a point charge Q over here and we have to find out the electric field due to a point charge at a distance r from the point charge. So we have already seen that in order to measure the strength of the electric field, we have to place a test charge here. So let's the test charge placed here at the point P where we have to measure the electric field is Q0. And we know that the force experienced by this test charge due to this source charge is given by the Coulomb law 1 over 4 pi epsilon 0 q0 divided by r square. And we have defined the electric field as the force experienced by the unit positive charge placed at that point. So the electric field intensity is equal to, and we know that the direction of the forces along r cap, the unit vector pointing from q to q naught. So this is r cap, or along this point. Suppose the test charge at this point A, then the unit vector is along AP. So E is defined as F divided by Q naught, which is 1 over 4 pi epsilon 0. Q naught and Q naught cancel. Q divided by R square vector R cap. So this is the electric field intensity due to a point charge Q at a distance R from the point charge, and it is measured in Newton per Coulomb. So now we discuss the principle of superposition. So suppose we have n number of charges, then what is the resultant electric field intensity? So we have a system of charges Q1, Q2, Q3, etc. up to Qn. These are the set of source charges Q1, Q2, Q3, Q4, etc. up to Qn. So now we have to calculate the electric field due to this number of charges. So for that, we have to calculate the force due to these charges on a test charge Q naught. So we know that the force obey the principle of superposition. That means the total force acting on this charge Q naught is the vector sum of the force due to individual charges. That means the force between the two charges of a system is unaffected by the presence of other charges. So first of all, we can calculate the force on the charge Q naught due to Q1. So this is termed as F1. Then we can calculate the force on Q naught due to Q2, which is F2. Then we can calculate the force on Q naught due to Q3, which is F3. So and we have to calculate the force due to each and every charge, and finally we can find out the force due to Qn on the charge Q naught, which is Fn. Then we can take the vector sum of all these charges. So this gives the net force acting on the test charge Q naught. So let R1 be the distance between the charge Q naught and Q1. R2 be the distance between the charge Q naught and Q2. And similarly, Rn is the distance between Qn and Q0. R3 is the distance between Q0 and Q3, and so on. So F1 is equal to 1 by 4 pi epsilon 0 Q1 Q naught divided by R1 square vector R1 cap, and F2 is equal to 1 over 4 pi epsilon 0 Q2 Q0 by R2 square R2 cap, and similarly Fn can be written as 1 over 4 pi epsilon 0 Qn Q0 by Rn square vector Rn cap. So the net force acting on the system is the vector sum of the force due to the individual charges. That is, capital F is equal to F1 vector F1 plus vector F2 plus vector F3 plus etc. up to vector Fn. And therefore we can write 1 over 4 pi epsilon 0 Q1 Q0 by R1 square R1 cap plus 1 over 4 pi epsilon 0 Q2 Q0 divided by R2 square vector R2 cap plus etc. up to Fn, which is equal to 1 over 4 pi epsilon 0 Qn Q0 divided by Rn square vector Rn cap. So from this we can see that Q0 is a common factor, and therefore we can write Q0 into 1 over 4 pi epsilon 0 Q1 by R1 square R1 cap plus 1 over 4 pi epsilon 0 Q2 divided by R2 square R2 cap plus 1 etc. up to 1 over 4 pi epsilon 0 Qn divided by Rn square vector Rn cap. So we can see that this is nothing but the electric field due to the charge Q1. So therefore this one is termed as E1. And the second term is nothing but the electric field due to the charge Q2. So which is termed as E2. And similarly the last term was nothing but the electric field due to the charge Qn, which is termed as En. So we can write this force is equal to Q0 times E1 plus E2 plus etc. up to En. But we know that F is equal to Q0 times E, where Q0 is our test charge. So Q0 into E1 plus E2 plus etc. up to En. So cancelling is Q0 from both sides, we get E vector E is equal to the vector sum of the individual electric fields. So which means that the electric field obeys the principle of superposition. So we can say that the resultant electric field acting at any point due to a system of charges is the vector sum of the individual electric fields acting on it. So this E here is equal to 1 over 4 pi epsilon 0 Q1 by R1 square R1 cap plus etc. up to 1 over 4 pi epsilon 0 Qn divided by Rn square vector Rn cap. So this can be written using the summation symbol. So 1 over 4 pi epsilon 0 is a constant over here, and we can write summation I goes from 1 to n Q I by Ri square vector Ri cap. So when I equal to 1, the term is 1 over 4 pi epsilon 0 Q1 by R1 square R1 cap. So when I equal to 2, the term is 1 over 4 pi epsilon 0 Q2 by R2 square R2 cap. When I equal to n, the term is Qn by Rn square Rn cap. So summation means the I is being summed over from 1 to n. So we have all the terms. So this is another expression for electric field intensity in terms of the summation symbol. So therefore electric field intensity obeys the principle of superposition. So the